show you when I get back. have to go to that weather center today
All right.
at the Aeon.
You went inside, right?
Yeah.
Crazy, they weren't actively making the snow, but I guess they did the day before or something.
So that was fun, huh?
Yeah. It really,
They do a lot of testing there.
Did they tell you how much it cost to build the facility?
Yeah, like 50 million or something
Yeah,
like
they
that.
spend a lot of money into it.
Yeah.
Very impressive. And I guess the owner take really pride in having something that unique in his own backyard.
I guess he said that every time they want to make snow like that, it's like $10,000 for them to make snow.
Yeah, but they get a whole new product certified and tested.
Yeah.
Yeah, you would expect something to be like this in in Carrier or, the other big guys. I guess because ON is not really the biggest, right? But they are, I guess, the special need manufacturer. Like custom made, I guess that's the right word. Custom made manufacturer. You should post the picture on our Facebook so that people know what they lost, what they missed today. Make them feel sad.
One of the guys showed up a little late, but he didn't get to initially go with us in there, so he's not in that picture. But I guess afterwards he asked if he could just go see it real quick, and the director said, it was cool. So
I really like the production line too, like for this like small water source heat pump that they make, and how it's just like really, it's all about sheet metal. I mean, they get the compressor from somewhere else and all they do there in production line is like really sheet metal, So that was also very interesting. And at the end, like when we went there, they showed us they have a unit for like open, they have this like model where they show you different parts and different component of it. And it's just for illustration for their customers. I love that one too. It was very educational.
I didn't get to go through all the production areas, but just the innovation center really is where we went.
But you didn't see the big production line where they actually make the heat pump was like coming out like, matchboxes, tuck, 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 tuck.
I wish, but no, we just went to the innovation center.
Okay. That's where they have the cutout models, right?
Innovation center or something?
Right in the second floor. Isn't that where they have the big heat pumps that you can open it and check what's inside? And
I might not have seen that area.
okay.
Maybe. Yeah, they just had, we've seen all the testing rooms, like their sound testing room. And they have all those little metal, it's like stainless steel. I'm not sure I forget what he called them, but there's a bunch of little cones hung on the wall everywhere.
Right. Danny crew.
Yeah.
But there is like on the second floor, there is like a place for the VIP guests to sit and watch the test being done.
Oh, yeah.
And that's the place next to it is where they have all those, they used to have those big units that you can open them and check what's inside them as illustrative models. Okay, maybe they changed the position. But I love the place also when they can rain. They can make rain on it.
Oh, yeah.
And they have all the drains to take the water out. There's a bunch of OSU students working there too.
They said they hire like half LSU students and the other half like Montana State where the founders from or something.
Okay. Yeah, I know at least 2 OSU students from my class that actually work over there.
Said they're hiring, we're supposed to be getting like 3 more positions too.
All right. Yeah, it's a very good place to work. They also have a lot of, they won a lot financially too, like all those medal for performance for their shareholder and stuff. They are doing really well. I think that's what they started the tour with. They show you all their accomplishment on the stock market and how much profit they are making for their customers, for their shareholders, or something.
Interrupt you more, but I'm not sure if this is something that you folks would be interested, or I don't even know if OSU would be interested in knowing this, but they said they had a lot of technician positions, like the lab technicians, just not sure if that'd be equivalent to like a research assistant around here or something, but
When? Is it open right now?
they said they had a lot of those positions open.
Okay. Well, this is something to send to all the SME students to let them know. Because this summer, maybe people will be looking for internship. And if your internship is to work as technician at ON, that is really a good place to train in the summer and build your resume. And once you graduate, you can get an engineering position later on. So I had 3 internships when I was undergrad. My first internship was assistant mechanic, working for, it was in the airport, but it was in the kitchen of the airport. There was this huge kitchen that make the meals for all the airplanes. That was in Cairo International Airport. And so there is this company that basically make food for all the airplane that lands. And that kitchen have big mixers and big furnaces, and they have mechanics on board just to fix everything. And I was the assistant of the mechanic. My job was to unbolt the furnace or the mixing machine for him. He go do his thing, and then he tell me, now hook it up. And so I just bolt again. So I spent my life opening screws, putting screws. And you would learn just by observing, but that was my first year. And I thought it was really fun. And the second year was in the periodic maintenance, where they bring the airplane deep cleaning it, open the engine, check every single plate with ultrasound. That was also fun. And then the third year was in a big power plant. And in every one of them, just seeing the equipment, that people use is really, really useful. All right, so let's start. It's 9:01. So can you guys confirm online that you can still hear me?
Yes, sir.
All right, thank you. So we're gonna talk about chapter 5 today, gas turbines. Okay, so gas turbines are really gonna be important in the future because they are the perfect companion for wind energy. Okay, I was one time visiting BSO power plant across the gathering place. And over there, they have the control room where they can show you all the energy coming in and out. And so the guy, we went early on and he was showing us how does the wind was so powerful, so before like in like sunrise. He said that when the people woke up, here's the wind. And you see the wind just kind of stopped. So renewable energy, especially wind, is not always consistent, right? And so you need something that can fill the gap very quickly. And so those are the two gas turbines that is actually Jinx power plant. Next to their big steam power plant, they have those two guys. Okay, and they tell you that the big steam power plant take 8 hours from when you decide let's get in to when it's making full power. 8 hours, take or lose a little bit. This guy is 8 minutes. This is 8 minutes from the let's start until it's working at full power. So that rapid kick in and its ability to work at different load is really, this flexibility is really nice. Okay. This big thing is just the air filter, and this is the chimney. Okay. This is like bunch of air filters so that you have a lot of surface area, you don't have pressure drop on them. You suck all that air, go into a compressor that's not shown over here, and then that compressor send the compressed air to all those cans. So all over the shaft, there are those cans are combustors. So you dump the natural gas on it, and the compressed air come, and you have the fire, and that exhaust leave and go to the turbine. The turbine run the compressor, and the extra energy left run the generator, and that's how you get your energy from. Okay. So it looked like this. I mean, he's drawing it as two turbine, and some of them are like that, where you have turbine sitting on the compressor, and the other one is basically free turbine or power turbine. And that's the one that run the load. That load could be the generator. That load could also be the helicopter rotor. That load could be the propeller of a boat, basically. Okay. Or maybe even a train. So whatever that load is, that turbine will run it. So this idea of this not jet engine, but gas turbine power train was like really, really old. It's just that they didn't make it work in the old time before World War II, couldn't make it work because the turbine was not efficient enough to run the compressor to start with, let alone have extra work left over. So until they managed to actually make this turbine enough to run this, and you got extra power that you can then jet it behind and generate thrust, or make it run something else and have a propeller, that's when the jet engine was created. So I'm saying is that jet engine was on paper for so many years before they actually make it work because of the inefficiency of the turbine and the compressor. Okay. So this cycle on a TS diagram will look like this. Isentropic compression going up. This is constant pressure. Heat addition, isentropic expansion, constant pressure, heat rejection. Okay? And not so popular, but the BV diagram would look like this. Okay, you can see the isentropic compression, the constant pressure heat addition, the isentropic expansion, and the constant pressure heat rejection. Okay, and so the thing that we need to know, the equation of state P equal rho RT, of course. That T need to be in Kelvin. That pressure need to be in Pascal, right? And that rho would be in kilogram per meter cube, and that R would be in joule per kilogram Kelvin. And our air is how much? Our air is 287, right? 287. And how do we come up with this R? R is, you remember R is R universal over the molecular weight, and R universal is 8,315 over the molecular weight of the working fluid that you are circulating. That working fluid could be air, but we will see at the end of the lecture that sometimes they run helium. If that gas turbine is not being run by burning fuel, but rather by cooling a nuclear reactor, that would be helium running in the cycle. And still it's a Brayton cycle. So what I'm saying is that the constant pressure heat addition doesn't have always to be let's burn stuff in. It could just be let's go and cool something really hot. Okay. So for example, rocket engine. What's a rocket engine? How is it different from a gas or a jet engine? What's the fundamental difference between a rocket engine that take you to the moon and a jet engine that fly you across the what? Yes, so the difference is the oxidizer. Where is it coming from? If the oxidizer is on board, you carry the fuel and the oxygen, that's a rocket engine. But if you are breathing the air and you are just carrying the fuel on board, so you just like put the fuel in the combustor, that's a jet engine. That's an air breathing engine. So one idea is, can't we make a rocket engine that's also breathing air? So look exactly like, except that some of the air is coming from the outside. But the problem is if you're flying super fast like this, and rocket engines supposed to fly really fast so that they can leave the Earth, we need to hit 11,000 more or less meter per second. 11,000 meter per second to be able to leave the Earth. Okay, that's a number to remember. So in order to get that high, the air, if you let the air into the engine while you are going through it, the air will be super hot. You cannot really combust in air that hot. So one of the idea is, can we cool that air inside the engine so that then we can let him get in? So the company that do this, and they actually build, they said we thought that we are starting like we are an aerospace company, but we turn ourselves or like spend all our time in the heat exchanger that cool the hot air by running basically something like this. It has a compressor and their combustion chamber is the heat exchanger that cool the air by doing helium over here. Okay. I will show you this cycle next time. It's really interesting. And it has like a bunch of Brayton cycle. Each one of them is cooling the other one. But the point is the heat exchanger doesn't, or the combustion chamber doesn't have to be burning fuel. It could just be cooling something that's really hot. And in the process, you get your fluid to be really hot, and he's ready for the turbine next. Okay. So that R that we just calculated is the difference between CP and CV. CP, constant pressure, and CV, constant volume, heat capacity. Difference between them is R. Okay. And then it follow that R is gamma minus 1 over gamma CP. Actually, I don't memorize it like this. When I was undergrad, I used to memorize it that CB is gamma R over gamma minus 1. Okay, and I'm saying gamma and it's K, but some books use gamma and some books use K. What is K and what's gamma? The specific heat ratio. Okay, so gamma is basically what? CB over CV. CB is always bigger than CV by R. So to recap what I just said right now, you got gamma, which is CB over CV. You got R, that is CB minus CV. And you need to remember that CB is gamma R over gamma minus 1. And therefore, CV is, what do you think CV is? R over gamma minus 1. Okay, so in case you don't know CB and CV, all you have to do is just do this gamma R over gamma minus 1. Okay, and of course, R is R universal over the molecular weight. And this guy is 8315 joule per kilomole Kelvin over M. So all you need is gamma and M, really. Okay, and that gamma is pretty much for diatomic gas is 1.4. What's diatomic? O2, N2, anything 2, that's 1.4. Okay, very good. So the other important formula is the isentropic expansion and compression. This going from 1 to 2 and going from 3 to 4. If you know the pressure ratio, you know that the compressor take you 5 times bigger than the initial pressure. Huh? And by the way, the turbine will take you the same ratio too, because I mean they work from the same pressure difference. The compressor take you from 1 to that pressure, and the turbine take you from that pressure back again to the atmosphere. Okay. So this is interesting because when we jump here to this picture, you will see here are the compressor plates. How many stages are there? A lot. Huh? 1, 2, 3, 4, 5, 6, 7, 8. And those are just the rotor, right? The stator are in between. The stator are on the casing, right? The rotor is the one on the shaft rotating, and between them is the stator plates, right? Remember when we talked about turbo machines at the beginning and how the rotor plate twists the air and the stator plate untwist the air and get them straight so that they go to the next stage? So the air is like basically twisting, untwist, twisting, untwist, twisting, untwist. And every time he get untwisted, he recovered the pressure. So the pressure build up in the compressor because of the stators. Because they straighten them up and raise the pressure, straighten them up and raise the pressure. And when they straighten them up, they send them into, what is that shape? Diffuser. They send them into a diffuser. So the pressure go up because the velocity is getting lower, because the area is getting bigger. When you send the flow into a diffuser, when you give him more area, huh? What happened? His velocity decrease and his pressure increase, right? So what I'm saying is that it will be as if he's moving into something like this when he goes through between two stator plates. So when you go to something like this, your velocity will decrease and your pressure will increase. Okay? Makes sense? And how do they do this? Because the inlet area seems to be the same as the exit area. Well, not really. So what I'm saying is, and we talked about this before, this is exactly this, because they are sitting, the stator plates or the rotor plate, they are sitting on two circles. So when you divide the circumference over how many passages you have, It's the same number at the inlet and the exit. But what is genius about this, we should be proud as mechanical engineers or mechanical and aerospace engineer, whoever invented this, is that this is the true inlet area. Okay? And if you go up like this, this would be the true exit area. And so you can see how this is really this. I mean that the angle is not that big because you cannot get very greedy on diffuser. This angle, need to be small. Otherwise, he will separate. He will not really do this and say, wow, look at the area, let me drop my velocity. No, he would say, I can't do that. I'm just gonna go in the middle and separate. And this is our nose, by the way. That's why in our nose, the air separates and we shoot far away. We exhale far away. But when we inhale, we fill the whole cone with air. So we exhale far away and we inhale from closer part. Okay? I remember this because when I was a graduate students, one of our courses was telling us I remember that question. The professor said, the movie Honey, I Shrunk the Kids is fundamentally flawed. Explain this based on the flow separation. And so I realized that if you get them that small, the flow become very, very laminar, and that separation will not happen. That separation happens when you shoot at very high velocity. So when you get that small and your nose is very tiny, the flow will not separate. And so your inhale and exhale stroke will be the same. And so those kids will basically just keep breathing the same air that they are exhaling. Okay. Anyway, back to I make you lost your track. So this diffuser, the area expansion is not that big, but it is. It is expanding. And that's why the pressure is building up. Okay. But the point I'm really trying to make over here is this. The point is, while you have all this many rows of compressor to take you from B atmosphere to B combustion chamber, which is this, look how many rows of turbine you need to go. Only 2. And yes, there is more expansion that will happen over here, but that's not the whole story. Even if this turbine take you all the way to B atmosphere and you don't expand anymore, you still will have more rows of compressors than rows of turbine. Why? Because while the diffuser, you have to be really nice with him and don't go suddenly. You have to do it slowly. And therefore, you need so many stages to build the pressure. The turbine is really like a nozzle. And so when the flow goes through a nozzle, does he have a choice? He can't. He cannot separate on you. He can do this angle, he can do this angle, he can do this angle, and the flow will just have to follow the wall. So when you expand him in a nozzle, he will do it. But when you tell him, let's expand, sorry, let's get compressed in a diffuser and let's do the spec pressure ratio because I want you to double your area, he would say, no, I'm not. I'm just gonna go in the middle. Okay. So, I mean, this is really, we can have more detail about this in experimental flow course. But that's why basically the flow does not separate at the upstream face of a Gulf ball, but separate at the downstream. Okay, so just to hound this idea in your head, you get stuck. You need to tell yourself, if I am watching the flow over a sphere like this, will the air ever separate or cannot follow the wall here? He has to. But at the other side, he actually will separate from this point. All this will be just like awake. Why he didn't? Why at the other end? Why he didn't really follow like this? Because it's so large pressure hill to climb. So to go like this, it will be like you're asking him to fill all that area. He can't. He can't take all this area again. He just will leave here. And of course, that is a problem for anyone playing golf or throwing a ball or anything, because that big wake at the back increase the drag. Right? So end of the story is going through a diffuser. So going in a diffuser, you have to be nice with the air. Going through a nozzle, he does not have a choice. You can force him. Okay? He will have to follow. He does not have anywhere else to go. He will have to follow through this. Okay? Good. So we need to understand this process, the compression and expansion. If we know the pressure ratio and the T1, can we calculate T2? And if we know the pressure ratio and we know T4, for example, or T3, can we calculate the other one? And the answer is yes, there is a relation for isentropic expansion or compression. And that relation is this. T over T is P to over P to power K minus 1 over K. So if you know the pressure ratio and one of the temperature, you'll be able to get the second one. Okay? I always, when I was a student, I was always confusing, is it K over K minus 1 or K minus 1 over K? Okay, and there's a way to remember it, but it has to, you have to remember another formula from thermodynamics, which will not really help. So I think maybe to save your time, just remember it from here. Okay, but I can tell you that it basically, you need to remember that CB is gamma R over gamma minus 1. Okay, CB is gamma R to gamma minus 1. And then you need to remember that for isentropic expansion, delta B is delta T to power CP. And so, and here is R. And so then CP is gamma R over gamma minus 1. So in the T side, it's gamma over gamma minus 1. And then on the other side, if you take it here, it's gamma minus 1 over gamma. But you can see this is a long route because you have to remember, first of all, this. And also you have to remember that it's CBT. And so that's too much to remembering. And besides, the exam is all in book. So let's just check the formula. But that's how I remember it in my head. All right. So now in this cycle, there is the air standard cycle is that air. Everywhere is air. And that heating happened by magic. Basically, just like a heat source give you the heat. Nuclear reactor give you the heat. Heat exchanger give you the heat. But in real life, that heat happened because of combustion. We are dumping fuel in. And so once we dump fuel in, you started here with air, but you end up here with not air anymore. You end up with air mixture, CO2 and H2O, and therefore the CP that you started with is probably different from that CP. Why? I thought CB was gamma R minus gamma minus 1. Yeah, but the gamma is different now. Rather than O2 and N2, you got yourself CO2 and H2O. That's a triatomic gas with completely different CP. Okay. Yes, there's a lot of air and the amount of fuel that you burn is very little, but still that changed the mixture. So if you want to be accurate, he is saying, well, you probably need to change your CB. Here is CB for air at the beginning, and here is the CB at the end. Here is the K at the beginning. Why 1.4? Because it was O2 and N2 air. But here is the CP, sorry, here is the K at the end, 1.33. How come? Because I have a lot of CO2 and H2O. Not all CO2 and H2O, but a bunch of them are there. Okay? So if you really want to be accurate for the turbine, you would use this. And for the compressor, you would use this. So while they are all the same isentropic relation, but they have different K on this side and on the other side. Make sense? Okay. And so now in between, while we are doing the combustor, if I want to analyze the combustor, first law of thermodynamics, Q dot that I add in the combustor is m dot multiplied by delta H. Okay, and that delta H is probably m dot Cb delta T. The delta H is going to be Cb delta T. What Cb should I use? Should I use the 1.004, 1.0045, or the 1.148, or something in between? And he say no, something in between. Because during this combustion chamber, you start with this, you finish with this, so a really nice CP would be something in the middle. And the key also is something in the middle. Okay, makes sense? So the air standard Brayton cycle, where the jet engine was originally built based on it, is the one that we just plotted. And as you can see, work compressor, H minus H, work turbine, H minus H, the Q, H minus H. So everything is H minus H. And all those H's will become, for the compressor or the turbine, how do I calculate this H? CB delta T, right? So for steam, if we are analyzing a steam or vapor compression cycle, where do we get the H? We go to a table. Knowing two property, knowing the pressure and temperature, you read the H from the steam table or the refrigerant. But for gases, you can do CBT, assuming you have a decent CP. What is a decent CB? A CB that approximates the range. So when you had all air, that's a good CP. When you had all gas, that's a good CP. When you are a mixture and you are changing your stage, that CP is probably never going to happen, but it's a good mathematical average between you started with this and you end up with this. Where are you in the middle? Right? So it's just like a good approximation that will give you the correct Q. Say that again, slowly.
If you have like a new, what's your ratio, you have your air to combustion gases, or you always take the ratio difference between those two and then add it to the bottom one, right? If you're pretty close CP or close.
So if you really want to get the correct CP, there is no mystery about it. It's really sigma YI CBI. It's a mixture of gases, and if you know what at every stage in the combustor, what are the component there, what's the mass fraction? You got this much CO2, you got this much H2O, you got this much O2, you this much N2. The CB of the mixture is sigma YI CBI. It's like, what is the average money per person over here? You basically just do you figure out how much money each one has, and you get an average. So that's what they do. So there are ways to do this really accurately. If you don't track every single place in the combustor, and you can see how the mixture changes property. But I bet this one is just based on, see, the average of air and combustion product. He basically said, at the beginning I have this, at the end I have this. He probably did mathematical average or something even. I mean, if this is 114 and this is 7. So just like basically just mathematical average. But I would say a good average would be the one that will give us, not a good average, a good number is the one that will give us exactly the right Q. So that when I need the CB for what? To calculate this. The Q is H minus H, HC minus H2. So if my CB can give me that Q fine, I'm okay. That's all its job to do. Efficiency is work net over Q added. Q added is here, and work net is work turbine minus work compressor. Okay. So he's replacing all the H's with CB, and because it's Brayton cycle, and that's the ideal cycle. What is the ideal cycle? The same fluid just circulating around. Nothing is being changing. Nothing changing it. No CB change. So he will cancel all the CB. Okay? The CB of the compressor, the CB of the turbine, the CB of the combustion chamber, they are all the same. They cancel them, they get like this, and you just follow the mass over here. You will find out that, let me just jump very quickly here. You will find out that the efficiency of that cycle is simply 1 minus T1 over T2. That is the efficiency. T1 and T2, T1 and T2. Okay? And that T1 and T2, that's isentropic expansion. That are related to the pressure ratio, to power gamma minus 1 over gamma. So the eta, the thermal efficiency of that gas turbine, at least the ideal one, without changing in CP, without any losses, is just the pressure ratio. So what that tell you? To have very high efficiency, you need to take the pressure ratio as high as you can. Okay, so the if you are plotting or like designing the cycle, here is the TS diagram, and if you have the air here at T1, and this is Tmax, huh? Why Tmax? Maybe your material, turbine material cannot take any longer than, any hotter than this. Anything hotter than this, we will melt. So, and I asked you to plot the maximum efficiency cycle. This is T ambient. So we're gonna come here, and this is Tmax. How does it look like? The maximum efficiency cycle ever. A square, but is it like that square? I still want to do a Brayton cycle, right? How it will look like. What is a Brayton cycle? I need to go up and then constant pressure, then down, then constant pressure. So how do you want me to fit that cycle inside that square? Like go, how? It will be this. Okay. This is why I'm doing that, because I want what I'm trying to achieve. I want to maximize the pressure ratio. I want to go as high pressure ratio as I can. That's maximum efficiency. Okay, you understand? You want to go as high as your T maximum allow you. Okay, but that cycle probably is not going to have a lot of work coming out. I mean, maximum efficiency, but there is something in between that will give you a lot of work. Okay, so, but the maximum efficiency is definitely the one with the highest pressure. So if we plot the efficiency as function of that pressure, obviously the higher this will get, the higher this ratio will get, the smaller this minus will get. And in the extreme case, if this guy go to infinity, this eta go to right. So it's basically keep rising like this. The efficiency with the pressure ratio, right? So they try to build higher and higher pressure, of course, but limited with the maximum temperature. But then people work on this maximum temperature. There's a lot of work on, and the way they can make those temperature, those plates take really high temperature is, yes, it's metal so that can be strong, but they coat it with tungsten carbides and like all those material that can really take very, very high temperature. Problem is this tungsten carbide and stuff, they are like ceramics. They are not really strong. They are brittle. So they just coat the plates with it. They make the plate out of metal and then they coat it with tungsten carbide. And when they coat it, they actually shoot those particles with supersonic speed so that they can get stuck to the plate. There's a lot of things that they do in order to make those plates really take the high temperature, especially that they're already under very high RPM. I'm talking about the turbine plates, right? I'm pointing to the wrong place. This. So they have to coat them with tungsten carbide, right? And they want to cool them from the inside too. They make a lot of holes and stuff in order to be able to cool them. So it's a tough heat transfer problem to maintain them working at very high temperature. And this is where the combustion chamber is. So the compressed air will come in, and then the fuel will be added in the middle. And then once you have the burner over here or the flame, you keep adding air to cool it. So by the time it leaves here, it will not burn the gas turbine plate. Okay, so the air that they add here is almost 4 times more than the air that's actually required to do the combustion. Why 4 times bigger? Because you want the temperature to be less than the temperature of that the flame actually can generate. You want to lower that temperature. Okay.
Is the TS diagram any different for multiple phase with M1, M2, and M3?
So if you have a lot of, and when they do this, they have like high pressure compressor and intermediate pressure compressor and low pressure compressor. And on the other side, there will be low pressure turbine, high pressure turbine, intermediate pressure turbine, and low pressure turbine. And they will make every turbine run each compressor, and you can have like 3 shafts running so that each pair run with their own speed, right? So when this happens, you will just climb in 3 steps. You climb, and then you climb, and then you climb. And you expand. Huh? Well, let's see how does it look like in real life. In real life, you don't go up like this. In real life, you have to go to the right. So that up on the compressor from 1 to 2, this is called 2S, 2 isentropic. The one that we will get with what T over T is B2 over B, gamma minus 1 over gamma, or K minus 1 over K. That's isentropic temperature. But the actual temperature will be hotter. The compressor will have the air a little bit hotter. How come? Why the real one will be here rather than here? And this is TS diagram. Why it has to be to the right like this? Because of it has to have more entropy because it's not reversible, because it's real process, not isentropic. Isentropic is adiabatic and reversible. So if you are adiabatic and reversible, your entropy not gonna change. Your entropy remain the same. But if you are adiabatic, and it's adiabatic because it's insulated, you are adiabatic because you are moving very quickly, you don't have time to heat transfer, it's adiabatic. But you have losses. You have eddy circulation, you have a lot of friction. All that irreversibility, second law tell you the entropy need to increase. Okay, so you are still going from B1 to B2, but because the entropy need to increase, you end up here. What does that mean? Yes, I got to the same pressure, but I got at higher temperature. Is that good news that I'm leaving the compressor at higher temperature? Is that good news or bad news? You may think it's good news because now the combustor is not going to work as hot, as doesn't have to heat as much. Yes, but it's really bad news for the compressor. Why? What's bad about this 2 compared to 2S? What's bad? What's work compressor again? CB multiplied by delta T. So originally the plan was 2S minus T1. Now because you end up here, the compressor work is T2 minus T1. that compressor will be harder to drive than the other one. And this opposite happened in the turbine. In the turbine, when we were expanding from 3 to 4S, why? Because adiabatic and reversible. Adiabatic, no heat transfer, it's insulated, there is no time to heat transfer. So you are supposed to go like this. But the second law tell you, wait a minute, you're adiabatic, yes, but you're not reversible. You have irreversibility, friction, separation at the wall. So what happened? Your entry has to increase. Now look at this. Amazingly, this time going to the right, the same be ambient. Make T4 higher than T4S. Is that good news or bad news? T4 is higher. Good news or bad news? Bad, because what? The work. Originally, you are supposed to have all this work. CB T3 minus T4S. Now you'll have only T3 minus T4. So the second law will tell you your compressor need more work than the ideal, and your turbine will produce less work than the ideal. And so there is no wonder why they couldn't make that jet engine fly in the old time. Turbine was like horrible, the compressor was horrible, the cycle couldn't really sustain itself. Okay. So now imagine if after we did this first, this was just like the first compressor, and we have another stage where we will start. We start from here. And the ideal will be going like this, but the second stage in real life will go like this. And then the third stage, we will be here and we're supposed to go like this, and then we'll go like this. So basically the cycle keeps shifting to the right as we go from the second stage to stage. Why? The entropy always need to increase. Notice that in the combustion chamber, when we go from 2 to 3, the entropy is increasing because of the heat addition. Heat addition increases the entropy. Just like when you go from 4 to 1, why does the entropy decrease now? I mean, it's decreasing. I'm coming from 4 all the way to 1. Why does it decrease? Because heat rejection. So the entropy change for 2 reasons. Heat transfer, period, heat transfer. You give him heat, entropy increase. You take heat, the entropy decrease. And irreversibility. Irreversibility always add entropy. So this fact is the reason why the second law said you cannot have a power cycle that take heat and produce work. You cannot have a heat cycle that take heat from you and produce work without heat rejection. That is a statement of the second law. You need to give heat back. Why? Because you are running on a cycle. So how would you return back to your original position so the cycle would continue? You need to reject heat. And the fact that you are rejecting heat, that means now that the Q added is get divided. You have to spend money on your son and your daughter. You cannot spend all the money on your son. You cannot spend all the work, all the heat and making work and have 100% efficiency. No, that Q added has to be some part work and some part heat rejection. And the best guy in doing this is Carnot cycle. So the efficiency is, for Carnot cycle, 1 minus TL over TH. Okay? And all other machines and turbines have to also do the same concept. You take heat, spend some work, and that's work net, by the way, right? And reject heat. And that's why efficiency is always less than 1%, 100%. Because of that simple fact that you have reject heat. Okay, so anyone who come and say I invented a heat engine that 100% efficiency, he is not in compliance with the second law. Okay. Good. So the going from 1 to 2s, we just use T over T is P over P, gamma minus 1 over gamma. And then to find this T2, what do? We say eta compressor. What's eta compressor? Small over big. So eta compressor will be this T2s minus T1 divided by T2 minus T1. What I'm saying is when I was a student, I used to do it in 2 steps. I will go from 1 to 2s and then go to 2. So the first step is to say to myself T2s over T1 is B2 over B1 gamma minus 1 over gamma, or K, what happened? Yeah. Okay, we do this. And then we say eta compressor is work, the small one over the big one, so that is efficiency. So the small one is the actual or the ideal? Which one is smaller, the ideal work or the actual work? The ideal work is the smallest, right?
Talking about
The compressor.
okay.
So it's work ideal over work actual. Okay, and so the work ideal is T2s minus T1, and the work actual is T2 minus T1. So this is known T2s, we got it. The only thing is T2. You get T2 from this. Okay, that's how I used to make it. But the book has a formula that is ready to use, and a lot of students just like to grab that formula and use it, and there's nothing wrong with it. Okay, so they basically they would use this to calculate T2. See, but you can see what is going on here is nothing but saying this is T2s over T1, and this is T2 minus T1. And this is coming from the efficiency definition, that it's the small work over the bigger work. So if you want to use this formula to calculate T2, that is great. And if you really want to know where is it coming from, it's those 2 steps that I showed you. Okay. But anyway, that formula then allow you to basically get T2 in terms of T1. Okay. And so that's how you can calculate work compressor like this. Okay, which is, what is this equation? This is nothing but CB, work compressor is CB T2 minus T1. I know you don't see it, but it's T2 minus T1, and then it's T2 minus T1 is actually T2s minus T1 over eta compressor. And then he take T1 out, and so he end up with 1 minus T2 over T2s over T1, and that is T2s over T1. So again, you can use this formula for work compressor, that's totally fine. Okay, but if you just want to memorize the actual fundamental equation, and it's simply work is CB delta T, that's it. Work compressor is CB T2 minus T1, and then you get T2 from using T2s and the efficiency definition, whatever is convenient for you. Okay, but that is work compressor with the pressure ratio and T1. Okay, and that's T2 in terms of T1. One time I just asked them to prove this for me in the exam, starting from those 2 equations. So I mean, it really helps if you know how did this formula come from? From the fact that work is CB delta T, and temperature ratio and pressure ratio for isentropic process are related to each other by that power relation. T over T is P over P to power gamma minus 1 over gamma. Okay. So here is an example where, you know, he will said, here is T1, sorry, V1 and T1 coming at 300, pressure is this much, the isentropic combustion efficiency is this, calculate the exit temperature of the compressor, T2, calculate the work of the compressor. Okay, so it's like basic substituting in the formulas. Okay, so the only thing that we can screw up here is the temperature. It has to be in Kelvin. You cannot keep the temperature in degrees centigrade. Okay, the pressure ratio, when it's like this, it doesn't really matter whether it's kilopascal or Pascal, but my advice is to stick to Pascal. And I told you about that story, funny story about me in the midterm, remember? When I was a student, and my brain kept telling me, we have to use Pascal. And the other side, like, are you stupid? It doesn't matter. You're gonna cancel the 10 to the power 3. And like, no, I have to do it. And then I was start like using the calculator, and my other side was like, are you crazy? Are you gonna multiply by 1,000 and you divide over 1,000? Did you totally lost it? I'm like, okay, I'm not gonna do this, but I'm gonna cancel it on paper. And I'm like, I cancel it on paper. My point is that it really pays off if you never touch anything weird, like kilopascal. I don't touch this. Degree centigrade, I don't touch this. I don't do those things. I don't even, my hand is clean. I always use Kelvin and Pascal. Then you don't do evil, basically. See no evil, do no evil. All right? So there is nothing special about this example. You can work. And the same thing in the turbine. Isentropic expansion and the actual expansion. Right? Same ratio between the temperature and the pressure. And here is eta, how it's relating the two temperatures together. And the work turbine, you call it work E for work expansion. Okay? And the temperature at the exit. An example that's just basically filling the number in the formula to calculate the work turbine. Okay, notice that when we say the work is CB delta T, what is the unit? Kilojoule per kilogram. This is specific work. What's missing is M dot. It needs M dot to become in megawatt or kilowatt or watts, right? All those are, and when we say that the Q added is CB delta T, that is specific heat addition. It's per unit mass, right? Yes? Okay, so now the equation that we need for the project, for the furnace, if we need this much heat in the furnace, how much natural gas do we need to burn? How much fuel do we need to consume? So that then we multiply by his flow rate. So we multiply by his price, basically. Okay, and so the equation in the heat addition process or the combustion chamber is Q added is M dot CB delta T. M dot CB delta T, right? Same like everyone, it's the first law. But this Q dot added is also having to be what? M dot fuel multiplied by the heating value of the fuel. So that's what turned the kilowatt or the BTU per hour that the swimming pool need into the mass flow rate of the fuel that you need. It's the heating value of the fuel. Okay. Of course, there is also an efficiency of the burner. Not all the fuel get burned. Okay, and different furnaces have different efficiency. And when you think about it, why would the furnace be not efficient? He let the hot gases leave early before they have a chance to lose all their heat to the water that they are trying to heat. So they may not have enough surface to really spend quality time. It's like a professor come in the lecture, spend 30 minutes and he leave. He didn't spend enough time with the student to tell everything. So if you don't spend enough quality time in the heat exchanger with the water you're trying to heat, you're not going to give all the heat and you will leave hot. Also, maybe he leave he just does not really burn all the fuel. The burner itself is not designed to burn all the fuel, and he's making like soot at the back. So for all those reasons, there is an efficiency over here, and the higher the efficiency, the more expensive the furnace is. So you can buy cheap water furnaces or water heater furnace, and you can buy very expensive one. Okay, and the expensive one are called what? Not condensing water heater. That they make the hot gases as cold at the end, like they consume, take everything from them to the extent that the hot gases leaving are so cold that the water vapor on them drop as water. It's like your car with the exhaust dripping water. The exhaust of the car tailpipe is dripping water. Why? It's so cold that the water vapor in it is basically just coming as water. Okay, so that would be the condensing water heater. Okay, so what is the typical heating value? For gasoline and hydrocarbon, it's like if you are burning like propane and stuff, it's like 40 to 50 megajoule per kilogram. Okay, megajoule per kilogram. And what's really nice about natural gas is that when they bill us, the natural gas company, when they bill us, they don't bill us like the gas pump. When we fuel our car, what do we pay for? We pay for, what's the bill say? How many? Huh? Gallon. You pay for the mass, right? You don't pay for the mass time the heating value. You don't pay for the BTU or the joules. You pay for the mass, and it's understood that that fuel should have that heating value, right? But for the natural gas company, they actually bill you for the BTU. They call it CERM. What's a CERM? It's like what, 1,000 BTU or like what, million? What? How much is a CERM? CERM to BTU 100,000. Yes. So one CERM is 100,000 BTU. So how do they do this? Well, they measure, of course, the flow rate. But they say our natural gas is having this heating value, then we are sending for you this much BTU. And they bill you for that. Okay, so this actually will make our calculation easy. We will just calculate on this side how much heat does the water swimming pool need, and it will be in joule or BTU or whatever. And you just calculate it on this side, not just m dot. You just calculate m dot times the heating value. You all you have to do is just divide over an efficiency. You divide over the efficiency of the furnace, because so woke up, people. If you are sleeping, woke up. This is important for the project. So let's imagine that that furnace is supposed to give us this much Q dot for the swimming pool. Okay? From all the losses that you need to make up, you figure out this is how much joule or BTU that you require this hour. From 11 until 12, I need this many BTU. Okay? So that, and so the water come, the natural gas or the fuel come here, m dot fuel, right? And basically leave. And so that Q dot swimming pool is also gonna be the m dot time the heating value of the fuel. So m dot fuel time heating value. This is equal to this. So that many BTU is what you will be built for. Okay, but this is ideally. So to make it actual, we need to bump it up by dividing over eta furnace. So the load that you need to provide divided by eta furnace, which will make it even bigger. So let's say you want 200,000 or something. You divide over 0.7 and you realize that I have to burn even more fuel, because not everything that I burn will actually burn. Okay, so in this equation, if you divide the m dot fuel over m dot air, bring this guy here, then this become the fuel to air ratio. And just doing the CB and the delta T and heating value, you realize that m dot fuel over m dot air is actually a very small number. It's like 4% or something. 4, 7, like it's basically does not take that much m dot fuel. So that's why jet engine don't have to carry a lot of things. They just carry the fuel and all the air is available for them. But rocket engine carry a lot of air. This is the typical heating value. You can see natural gas 46 megajoule per kilogram. They are in the 40s, right? So things are around 40. Ethanol is 26. It's just an example here to calculate the fuel to air ratio. All right. And the heat rate, what we said before, right? 1 over the eta, but you multiply by 3,412. So I just want to show you one table here before we leave, and we can continue next time. This table. Look at the heat rate in BTU per kilowatt hour. We said like 10,000 and higher, that sucks for a steam power plant, right? And when you go less than 10,000, that makes them happy. So you can see that some of the gas turbine, I mean, it's not really that big, 22 kilowatt, right? But you can see that they can have decent heat rate, not that bad. Right? So don't look down to gas turbine. I guess next time we'll talk about how you can make the efficiency even better, what can be done in the cycle to make it really better. Thank you for now, and I'll see you next week. By the way, next week is the midterm. Is the second midterm next week, right? And so it's 1 hour exam, and we are not going to have today in the midterm. So only the stuff that we didn't have in the first midterm. So what is the stuff that we didn't have in the first midterm? Solar. Or the solar is going to be in the midterm. Geothermal. So solar and geothermal is in the midterm. Questions? All right. Thank you.
So this gas turbine will not be in the midterm?
The gas turbine is not going to be in the midterm, right? And I'm going to post the solution. We didn't really have time to look at the solution of the homework, but it's pretty straightforward because it's exactly like the example in the book. But I'm going to post the solution anyway. All right? So solar and geothermal, all right?
Will there be a lecture before the exam?
Yes, we'll have a lecture and then 1 hour exam. That's correct.
Thank you.
Homework.
No homework. Yes, let's just focus on the exam. No homework this week.
Thank you, Dr. Salam.